Okay, so now let's move on to the blue problems, and they're very similar to the yellow problems, except they're in a different order and some of the numbers have been changed a bit. So we're now going to, so we go to problem 1, and we're going to let omega be the region of the xy plane bounded by these two curves, y equals x minus x squared, and y equals x squared minus 5x. And we're asked two things. We're asked to sketch the region, omega, and clearly labeling all the points of intersection. And then we want to use double integration to find the area of omega of the region. So let's get started. So the curves will intersect when the two values of y are equal. So we subtract those two expressions using this. And we can see that the result is a quadratic polynomial with zeros x equals 0 and x equals 3. So they're the x values where the curves intersect, and we need to find the values of, well, we find them using this, and then we need to find the values of y, and we can find those using this. Okay, so the points of intersection are 0, 0, and 3 minus 6. So we can plot those two curves as the red and the blue ones, respectively, using this. And this is what the region looks like. So the red curve is the upper curve and the blue curve. And the way to do that is to write down the double integral. So we first integrate from the blue curve up to the red curve with respect to y, and then for each of those we integrate with respect to x from 0 to 3. So this is the answer, or this is the integral. It's from x squared minus 5x, which is the lower curve, the blue curve, to x minus x squared, which is the red curve, and we can do that in a couple of stages. So we first do the y integration using this, and now we do the x integration using this, and the answer to the problem is 9. So that wasn't too bad. So let's go on to problem 2, and this is about a differential equation, this one here, and which involves, it's non-linear involved, and we're asked to solve it using this substitution or transformation. So let's get started. Well, we first of all have to establish the differential equation, and we can do that using this. And we can establish an equation connecting the new function v of x with y of x and x using this. And then we can solve that for y as a function of v using that. And then we need to differentiate that. And we can do that using this. No, we'll do it in the opposite order. So that's the reverse transformation, and this is the derivative of the original one. So now we put those into our differential equation for y, and we should get a differential equation for v, and we can see that's the case. There's no y anymore. And let's simplify that a bit, which we can do using that. And we can see that this factor, because this is equal to 0, this factor x squared will go away. This part here involves only v of x, it doesn't involve x, and this part here involving the derivative has a factor x. So if we divide this equation by this, and then divide the result by x, it becomes separable. And we can do that. The result of doing that is this thing here. So now, this equation is not only separable, but we can see that if we integrate it with respect to x, we can integrate this term without any difficulty, and we can see that the top, or the numerator of this second term here is proportional to the derivative of the denominator. So let's integrate that equation with respect to x. So we take that differential equation, integrate it with respect to x, and add a integration constant. And there we have it. And we can solve this equation for b of x using this, and we'll get two solutions like that. And now we need to express the solution for y of x, which is the original differential equation, and we can do that using this. So we can see there are two solutions, and whichever one's relevant will depend on the initial conditions. So there we go. That's the solution of that one. Let's move on to problem 3. So problem 3 is about a solid S in 3 dimensions, which is bounded below by a paraboloid whose equation is this, and above by a paraboloid whose equation is this. And we're asked to show that they meet on the circle, this, whose equation is this, in the plane z equals 1. The next thing is we're asked to sketch the solid, and then by evaluating an appropriate double integral in polar coordinates, we've got to find the volume of this solid. So go to the solution, and we can establish these two equations of the paraboloids using this. And to show that they meet on this circle, if we subtract these two equations, then z will disappear, and we'll get a place where the two paraboloids meet using that, and we can see that that is indeed 0 when x and y lie, when the point lies on that circle. And from this equation we can see that if x squared plus y squared is 1, then z is 1. So that solves the first part of the problem. Now we're supposed to sketch the surface, and we can do that using this. And the red equation is the first one, and that's the lower paraboloid, and this is the upper paraboloid. And if we turn this over a bit, we can see that the boundary of the solid is circular. So this region has cylindrical symmetry, and therefore polar coordinates are indicated. So let's go on and work it out. So the transformation from Cartesian to cylindrical polar coordinates, x goes to r cos theta, y goes to r sine theta, and z stays as z. So that's the transformation. And we need to, if we can't remember it, we need to work out the Jacobian of the transformation, and this is how you calculate the Jacobian matrix. You differentiate the vector of Cartesian variables expressed in polar form with respect to the three variables r, theta, and z. And so there's the matrix. And the factor is, of course, related to the determinant of, or the factor that goes into the integral is related to the determinant of that matrix, and we can calculate that using that to see that it's just R. So, and now we want to do the integral. So, if we do it in polar coordinates, we will have an integral around a circular region, and then we will integrate with respect to z from the value of R from here up to here, and then finally we'll integrate with respect to R from 0 to 1, where because that's the radius of the circle. So we need to find out the values of z on the upper and lower, or the lower and upper surfaces, and this is what they are here. Well, the volume of that region can be expressed as this integral. So we first, well, there's the factor coming from the transformation, and we first integrate with respect to z from the bottom to the top, and then we integrate the result of that with respect to R from 0 to 1, and then we finally integrate with respect to theta from 0 to 2 pi. Well, theta doesn't feature anywhere here, so that theta integration is easily done to just give 2 pi. And we can carry out the z integration to give this result, 2 pi, and then there's only the R integration left. This in here is just the value of this minus the value of this. And then the integral is pretty straightforward. We can do it using this, and we find that the volume of the solid is just pi. Problem 4. So we've got a thin triangular plate is bounded by the line x plus y equals 3 and the coordinate axes. And then, without calculating integrals, write down the area of the plate, and B, find the coordinates x tilde y tilde of the centroid of the plate. So let's get on with that. Let's define the equation of the line, and then we can solve that with respect for y, and then we can plot that region, or the plate looks something like that. And you see it's a triangular region, and the length of the base is equal to the length 3 of the height, so its area is just 3 by 3 divided by 2, which is 9 over 2. So we want to find the coordinates of the centroid now, so that will be 2/9 of the integral of a point in the region over the triangular region. And we can most easily do that by first integrating with respect to y from y equals 0 up to the line y equals 3 minus x, and that will give us this integral. And then when we've done that, we want to integrate the result from 0 to 3 with respect to x. Well, the integral with respect to y can be carried out pretty straightforwardly using that. So this just gives x times, there it is. And now we can carry out the integral over of this function here using this. And there we go. And that says that the coordinates of the centroid is the point 1, 1, and you can see from the figure that those two coordinates must be equal simply by the symmetry of the problem. So I think we'll, no, let's continue and finish. So the next problem is concerned with a differential equation, which we can establish using that, and we can see that it's a linear second order differential equation with constant coefficients, and that it's inhomogeneous because it also contains this forcing term. So we're asked to find the homogeneous solution, and we're asked for what value of this frequency omega here will the solution exhibit resonance. So let's get on with that. So we can establish the homogeneous differential equation by setting omega equals 0, so that's what it looks like, and we try and find an exponential solution of this form, which we can differentiate twice using this, and now we can put that into the homogeneous equation, and we see that we get an equation for the parameter lambda. And well, first of all, a can't be 0, because if a was 0, the solution would be 0. And then secondly, it involves the factor e to the t lambda, and that can never be 0 either. So we conclude that lambda squared plus 4 must be 0, and that's a quadratic equation, and we can solve for that using that. So we get two values of lambda, 2i and minus 2i, and so they're imaginary, so that means that the solution of the homogeneous equation is periodic and can be expressed as a linear combination of cosine of 2t and sine of 2t. So that's that. Well, when will that exhibit resonance? Well, it'll exhibit resonance when the frequency of the forcing term here, 2 pi omega, is equal to the natural frequency from the homogeneous solution. So that will occur when omega is equal to 1 over pi.